Okay. So, in fact, a first or an nth order linear ODE may be converted to a system of n first order ODEs, which was discussed in our previous lecture. Good? So look, let us show that, recall that one, an nth order ODE is of the form. Please recall the form of nth order linear ODE 1. So, which is best? Yn, A1 of t, Yn minus 1, A2 of t, Yn minus 2, N minus 1 of t, y prime, N of ty is d of t. As you see, this is the reduced form of an nth order linear ODE. Reduced form because the coefficient of nth derivative term is unity, as we stated previously. So this is the equation 1. Okay. Now, to show that our claim is true, that is, this single equation, there is only one equation, linear equation, which is of order n. Now, our claim is that it can be written as a system of n equations of the first order. Okay? So to do that, let it know. So indeed, look, introducing the functions. Well, I will introduce this function, x1 of t. Say y of t. Okay? Look, so this term, y, the solution itself, is denoted by x1 of t. Look, and we introduce a function x2 of t, which is the derivative of the solution. Okay? So this is x1. Look, we denote y. It is a function as x1. We then denote y prime as x2. Continuing in this way, look, by x3 of t, we denote by y double prime. So y double prime is a function which is denoted by x3. And continuing in this way, we see that x n minus 1 of t is taken as the n minus second derivative of y. So this term, this is denoted by x n minus 1, okay, in the general form. And finally, by xn, we denote the n minus first derivative of this solution of the linear equation, which is a single equation, but it is of order n. Okay? So introducing the functions x1, x2, x3 in this way. Good. Now, we have the following system. following system of n first order ODEs. Look, as you see, x1 of t has a derivative. What is the derivative of x1? It is x2. Yes, x1 is nothing but y. So its derivative is y prime, which is taken as x2. So we have x2. This is the first equation. Now, similarly, x2 prime, okay, is x2 is y prime. Its derivative is y double prime, which is x3. Okay? So we have this x3. And continuing in this way, we have shown that x the derivative of x n minus 1 will take the derivative of x n minus 1. X n minus 1 is this n minus second derivative of 1. Take its derivative, we get 1 n minus first, which is xn. So we have xn. So up to now, from 1 to n minus 1, we have n minus 1 equation. And the last equation, and finally, look at the equation itself. From the equation itself, the derivative of nth derivative of y is nothing but xn prime. Xn prime is the nth derivative of y, because it is already n minus first derivative. On differentiating, we have this x n prime. This is nth derivative of y in the original linear equation is xn prime in this setting. And this one, n minus first derivative is xn. Therefore, from the equation itself, we see that xn derivative of xn is given by minus n x1. Okay, this term written on the right hand side, minus n minus 1 x2. Of course, for symbol economy, I didn't write that n is a function of t, but in general, we know that the coefficient functions a1, a2, an are functions of t in general, minus this term, a2 times x3, a2 times, sorry, xn minus 1. Okay, let's put some dots, minus this term, a2 times xn minus 1, and minus a1 xn plus d of t is xn prime. And finally, so we have this equation. Xn derivative is given by minus an x1 minus n minus 1 x2 minus n minus 1 a2 xn minus 1 minus a1 xn plus d of t. Okay? So look, we have n first order ODE in the unknown functions x1, x2, and xn. Now, this is a system of the n-1 equation here, n-1 first order ODE plus the nth equation here gives a system of n first order ODE. So, look, if we solve, there is a one-to-one correspondence between the system of n first order ODE and the single linear ODE of order n. In the sense that, look, if we solve this system, okay, what is the meaning of that? Unknowns are functions x1, x2, up to xn. If we solve this system, it means that we derive x1, x2, xn. But look, x1 is nothing but 1. The required solution of the nth order linear ODE. Good? So if we solve this system first, finding all unknown functions which are x1, x2, xn, okay? The first function x1 is y of t, the required solution of our linear ODE of order n. Conversely, if we solve this single ODE of order n, we get 1, which is x1. So taking the derivative of x1, okay, we get x2. Taking the second derivative of 1, we get x3. Taking the n minus first derivative of 1, we get xn. So we get the solution of the system. Good? As you see, because when I say we find a solution, for 1, we mean a solution for a function which is differentiable up to order n. So taking its n minus first derivative or derivative up to order n is guaranteed, or differentiability is obvious because y is the solution. And the solution must be differentiable at least up to order n, which is a classical solution. Okay? So look, in the vector matrix form, let's write its solution. As you remember from a linear system of nth order equation, in matrix vector form, a system or a linear system of n first order or D may be written as, look, we define a solution vector. Look, with this tilde under x, I denote a vector or matrix variable, or a quantity which is vector of a matrix. In your textbook, such quantities, vectors or matrices, are written in bold-face type letters. So, by hand calculation, okay, I write that tilde notation to denote that the quantity under consideration is either a vector or a matrix. So I define this vector function. This is an n vector, okay? A vector function with n component functions. So these functions x1, x2, xn are considered as the coefficients of the vector function, as we did previously. So by this vector function x tilde, okay, we denote this vector function of order n. So this is a vector function of order n, okay? With this definition, look, so its derivative, as you remember, the derivative of a vector function is a new vector where the component will take the derivative of component functions. Therefore, it is this, or even like this notation may be used, dx dt. We can take the derivative of a vector, I mean that x1 prime, x2 prime, xn prime of t. Of course, it is an n vector value function. And now it is easy to see that our system now takes the form. Look, in matrix vector form, we have that x1 prime, x2 prime, xn prime. Yeah? Look, this is the left-hand side of an equation written in vector form. And the right-hand side may be written as a vector, which is the product of a matrix and the vector. Which one? This one. Multiplied by vector x, x1, x2 with components x1, x2, xn minus 1, and finally xn, plus an additional vector function containing non-homogeneity term. Good. Let's write one more, xn minus 1, xn prime. So, to obtain the first equation, we call the matrix vector product. What we have, no x1 term. Look at the first equation. The right-hand side is just x2. So when we perform the matrix vector product here, we have to get the first equation of the system. So since there is no term proportional to x1, so the first entry of this matrix to be later coefficient matrix of the system must be 0. So 0 x1, then 1 x2, look, 1 x2. So this must be 1. Then there is no other term, therefore all other entries on the first row of this matrix will be 0. So plus there is no non-homogeneity term, so here is 0 again. Good. So look, actually, when we perform the matrix vector product, so the first row will give x1 prime is x2. So the first equation of the system. Now, second equation tells us that x2 prime is x3. So look at x2 prime. So there is no x1, so 0. No x2 on the right-hand side. But there is a term proportional to x3. So this term must be 1. Good. And all other entries must be 0. Good. This is the diagonal term on the main diagonal, okay, of the matrix. Now, look at the n minus first equation of the system. So the derivative of xn minus 1 or xn minus first must be xn. So 0x1, 0x2, we call matrix vector division. So 0 xn minus 1, and finally 1. Good. So 1 times xn, which gives xn minus first derivative, and the last equation. So xn prime, look, we have x1, x2, xn, and a non-homogeneous term. So x1 is multiplied by minus an. Good. x2 is multiplied by a n minus 1. And continuing this way, xn minus 1 is multiplied by a2 minus a2. And xn is multiplied by a1. Good. So, and we have b of t plus b of t. So plus term is b of t. And observe that all 0 up to the n minus first entry of component function here, and finally we have b of t. Good. This is the system representation of 1. I'm not sure, but we may denote it by t. Okay. So, in short form, look at that. This is the derivative of vector. Now, putting tilde, I mean the vector function with n component functions. And its derivative is equal to, now, this matrix is clearly a matrix, a square matrix of order n. So, I write it as A tilde. They imply that it is a matrix quantity. Of course, it depends on t, because remember that these coefficient functions may be functions of t. Good. So, coefficients, although the coefficients up to the n minus first row are all constants, either 1 or 0. The last row entries may be functions of t, which are the coefficient functions in the linear equation. Good. So multiplied by, and this is the vector function x, the solution vector, plus we introduce a new vector, which stands for, which makes the system as a non-homogeneous one. So this is what? This is precisely the system of n first order non-homogeneous equation that we discussed previously. Okay? So now the theory established for such a system can be adopted to the first order linear ODE, keeping in mind this one-to-one correspondence. I'm repeating once again, look, if we solve this system with this specific coefficient matrix, good? Of course, in general, this coefficient matrix have each entry may be a function of t, but this is a specific structure. This matrix has a specific structure which corresponds to a single linear equation of order n. Yes. So in general, of course, the coefficient matrix in a system contains n by n entries, n by n times entries, which may all be some functions of t. Okay? This is a specific coefficient matrix, okay? And it is a representation or a system representation of a single linear ODE of order n. Good? Now, let me recall some very well-known results. What is known for this system? Let us write the some known results. For the system in T. Okay? Say 3 mark 1. In general, look, in general, the system of form T has a coefficient matrix. Which is something like that. A11 of T, A12 of T, A1n of T, A21 of T, A22 of T, A2n of T, and AN1 of T, ANN of T. Good. So in particular, as you see, in the system which corresponds to a linear n-ordered single ODE has a coefficient matrix, okay, whose row entries up to row n-1 are all constants, either 0 or 1, and the last row are minus A1, minus AN, minus AN minus 1, and so minus A1 is ANN, for example, in the general system. And we know that, we learned that such a system with a general coefficient matrix has a solution, okay, which is valid on some t interval, yes, from alpha to beta, an open t interval, where this coefficient matrix is continuous. And the continuity of a matrix can be determined by the continuity of their entries. So, look, if all entries of a matrix function or matrix value function are continuous on some t interval from alpha to beta, then the matrix function will be continuous. Okay? So, look, we know that, let's write this result here. uh, it is known that it is known from the theory, from the basic theory of linear systems. Systems that T has a solution valid on this interval, valid on T interval, where the coefficient matrix A of T and B of T, this vector valued function, which is a specific in the case of in the system representing 1. As you see, this coefficient, this non-homogeneity term has entries, 0 entries up to order n minus 1, and B of T is the last component function. Okay? So where the coefficient matrix and B of T is non-homogeneity vector function are continuous, are both continuous. This is the existence of solutions. Existence of solutions of T, of a system. So we already learned from the basic theory of the systems that whenever I'm talking about the general system, we discussed previously, if we find an interval of T where all entries of all components or all elements of this matrix are continuous, then the matrix coefficient is continuous, and therefore there exists a solution of the linear system written formally in phi, a solution valid on this interval. So this is nothing but the first existence theorem we introduced for the linear single ODE. Recall that we say that this linear equation has a solution, yes, which is valid in some T interval, say from alpha to beta, where the coefficient functions are all continuous. Now, look at the coefficient matrix representing this single ODE. The coefficient matrix are continuous when the last entry, when the functions of the last entry are all continuous, which are nothing but the coefficients of the linear and order ODE. So the continuity of matrix A depends on the continuity of the function of the last term, which is the statement of the theorem we give for the single ODE. Yes? So there exists a solution. So we just define the existence part of the solution of the linear equation, which requires finding a T interval where the coefficient functions, of course, and whenever when it is non-homogeneous, B of T is continuous. Okay? May be justified using the existence of solutions of such a system, which is very well known. Okay, what else? Look, as another remark. we say something about the structure of the solutions. Let's write it as another remark. Say remark 2. Structure of solutions of, let's say, 3. Without loss of generality, first we consider the homogeneous system. Homogeneous system, which system? X prime is A of Px is the homogeneous system corresponding to this more general system. So I assume that the vector value function p of p is 0. So each component function is 0 to give this homogeneous equation. And in fact, considering this homogeneous system does not cause any loss of generality, because we learned that if we solve this system, homogeneous system, successfully, it is not difficult to obtain the general solution of a non-homogeneous system. Thanks to the method of variation of parameters, we introduce it later again for the single ODE. First, consider the homogeneous system. X prime is A times X, okay? Where P of T is taken as the 0 vector identically. Now, again, it is known from the theory of N for the linear system. Again, it is known from the theory of N for the linear system that there exists N linearly independent vectors. Of course, I mean vector functions or n vector functions, independent vectors, such that the, let's say, first vector function. Okay? This is not the derivative. This is a matter of notation. This is the first vector function, denoted by this. Something like that. Okay? This is a vector. So first component is x1. But it is the first component of the first vector function. Then x2 of 1, second component of the first vector function, and finally n component of the first vector function. Of course, these are functions of t. So this is an n vector function. So there exist n linearly independent vector functions. First one is this. Second one, similarly, is second vector function. I. So in parentheses 2 denote the second vector solution. Components may be written again, first component, but first component of the second function. Second component of the second function. And finally, nth component of the second vector function. I hope that this looks well on your screen. Okay. And finally, look, a vector function, which is the nth vector function, with components x1 again, x2 again, and xn again. But these are the components of n vector solution. Good. N by 1. So we learned that for the homogeneous system, corresponding homogeneous system, there exist n linearly independent vectors. Good. So that you can think that these n vectors generate a basis for the vector space under consideration, or you may use the linearity to say that if this is a vector solution of the homogeneous system, yeah, then any combination, okay, of these vectors is also a solution. Okay? This is the superposition principle, so that the general solution, of the homogeneous system, Ax, okay, is of the form so x of t. So the general form of the solution of the corresponding homogeneous system is nothing but the linear combination of these n vector functions. Something like that. C1, x1, of course, as a function of t, C2, x2, and Cn, xn, by linear superposition principle. Since this is a linear system, okay, linear superposition principle, that's where C1, C2, Cn stands for arbitrary linear combination constant. Good. So this is known from the theory of linear systems. Good. Recall. Now, if we are interested in finding the solution of the single linear ODE of order 1, of order n in 1, so our first equation, we just need to find the first component of this solution. Remember, the first component of this solution is 1. We call the correspondence between this system, okay, and this single n for the linear ODE. The first component of, if we know the solution of the system, the first component is nothing but the required solution y of our nth order linear ODE. So writing the first component, yeah? Now, so recall here that with the first component of this vector function, look at the vector solution. This is x vector. Good. The first component x1 is nothing but 1, the required solution of the single ODE. And let's write the first component. The first component, let's say this solution, say 4. The first component in 4 is nothing but the required solution. Required solution of the homogeneous linear ODE, linear single ODE of homogeneous part, of course. Homogeneous part, single ODE in 1, which is, look, x1, yes, the first component is x1, which is y. And y represents the solution of the single nth order linear ODE. Let's write the first component. First component is written as C1 with x1, 1 of the first component of this. And taking the sum of n vectors, the second one is C2, x1, 2 of t, and continuing in this way. The first component coming from the last vector or nth vector solution is x1 of n. So look, of t. Good. So if we denote, look, this is not a good notation. x1, 1. I mean the first vector or first component function of the first vector solution. So let us denote it by y1, of course, as a function of x2, 1 is the first component of the second vector solution of the system. Let us denote it by y2. Okay? And this one is the first component of the n vector solution. Let us denote it by yn. Good. So with this notation, so now we justify that. Now we have just shown that the required solution, of the homogeneous, underline this, homogeneous linear ODE of order n say this one. Look, we call the operator notation. So the homogeneous equation can be written in this form. Has the form. Look, y of t, that is, I mean x1, because if we find the solution of the system, then we get the solution of the nth order ODE. I just consider the homogeneous part now. So with this notation, it is something like it. Good. Now, the structure of the homogeneous linear ODE must be the linear combination of n solutions, which are all solutions of the homogeneous equation. Okay? Look, such that L, Y, I must be 0 for I from 1 up to n. Okay? So y1, y2, yn must be solutions of homogeneous equation, but they should be linearly independent. Okay? So, if you recall that, now, if you recall that the solution of the system, homogeneous system, is written as a combination of these n functions. Okay? So, also, recall also that the solution of the system, of the homogeneous system, of n first order ODE may also be written as I'm writing the solution of the system again, which is the combination of that. Let's write once again. It is the combination of n vector solutions Cn xn of t, which may be written as a matrix times vector. Okay? Which may be written as that. Where C of t is called a fundamental matrix. Fundamental matrix satisfying the matrix equation. Satisfying the matrix equation C prime is A of T C Good. So this is a matrix equation. Yes, there's the matrix on the left, and the matrix n by n matrix multiplied by n matrix, another matrix on the right hand side, with the same coefficient matrix of the system. It is the same as the coefficient matrix of the system. It is called a fundamental matrix, okay, whose columns are vector solutions, whose columns are n linearly independent vector solutions. Look here. Here are n linearly independent vector solutions. So a fundamental matrix is of the form x1, x2, xn. So first column is nothing but, as you see, the first column is, this is x, first matrix solution, first vector solution of the system. Similarly, the second column is x1, 2, x2, 2, xn, 2. That is, it is the second vector solution. And continuing in this way, the last column is x1 and x2 and xn n. Okay? That is the last vector solution and vector solution. So we form a fundamental matrix like that and multiplying by C. C is a vector containing the linear combination constants, which is an n vector containing arbitrary linear combination constants. Actually, multiplying this matrix and vector C, we get this solution. Good. And what is known, because the columns are linearly independent vectors, okay? The determinant of this fundamental matrix, okay, called Wronskian Determinant, is non-zero for all t in this interval, where the coefficient matrix A of t is continuous. This is very well known from the basic theory. So now, you can say that these functions in the solution. Now, let us return back to the solution of, let's say, asterisk. This is the solution of nth order linear ODE. I mean, the homogeneous part of the linear ODE. We can claim that y1, y2, yn are linearly independent functions. Okay? Actually, look, it is possible to show that now the functions claim is a claim, the solutions yi of t for I, 1, 2, and are linearly independent. For any t on alpha beta interval. Indeed. How can we check the linear independence of n functions? Look, we write this equation, C1, y1 of t, C2, y2 of t. Indeed, consider that. Cn, yn of t. So given some t, okay, we require that this is 0, okay? Only when C1, C2, and Cn are all 0 for linear independence. Okay? Otherwise, if you find non-zero C1, C2, Cn, at least one is non-zero, then satisfying this equation, then y1, y2, yn are linearly dependent. Now, if this is the case, so look, because our functions are at least n times differentiable, okay? Consider also this equation. Yes, you can take the derivative. Taking the derivative of both sides, we get that. And it is justified, we justify in writing this because we know that y1, y2, yn are all differentiable functions. And continuing in this way, you can take the second derivative. Yn double prime of t is 0. And finally, you can take n minus first derivative. Yn n minus first derivative is 0. So we get n equations in n unknowns to determine C1, C2, and Cn. And observe that this is a system like, so this is a system like so in matrix form, the last system is this. Y1, Y2, Yn. Here is C1. It is a homogeneous system like this. 0, 0. Good. So the second equation implies that we have y1 prime, y2 prime, yn prime. And the last equation implies that y1 n minus first prime, y2 n minus first prime, yn n minus first prime multiplied by this is, okay, is 0. So to check the linear independence of n solutions, y1, y2, yn, of the linear f of the ODE, we may use this system of n equations, which is a homogeneous system for C1, C2, Cn. So, such a homogeneous system has a unique solution. It is known from basic linear algebra that such a homogeneous system has a unique solution if the determinant of the coefficient matrix is non-zero. That is, if the coefficient matrix is invertible. And look now, from linear algebra, from basic linear algebra, this system, the homogeneous system, has a unique solution which is in fact a trivial solution. Okay? Trivial solution. C1, C2, Cn are all zero. Okay? If and only if the coefficient matrix is invertible for some t. The coefficient matrix is invertible for some t0. Okay? But what is the coefficient matrix? Look, so that the determinant of the coefficient matrix, look, this is nothing but C. Okay? For this system, because the derivative of y prime is x2. Therefore, we have this. The coefficient matrix is nothing but the fundamental matrix in the system representation, whose determinant is clearly non-zero, because the columns of this fundamental matrix are linearly independent vector solutions of the homogeneous system. Okay? So this is guaranteed, and therefore this system, this matrix is invertible. So such a homogeneous algebraic system has a unique solution, which is the trivial solution. So by the definition, this combination is zero only when all coefficients C1, C2, Cn are zero, implying the linear independence of these functions. Okay? Now, we introduce a little bit new notation for this determinant. We introduce a notation. We introduce the notation. As you see, this is the determinant of C fundamental matrix, which we denoted by omega. So we introduce a notation for omega. Notation. Wronskian determinant of n function. Yes, I'm talking about the Wronskian determinant of these n functions, which are the independent solutions of the homogeneous system. So we introduce this notation for the Wronskian determinant. Of course, it is a function of t in general. So it is as y1 of t, y2 of t, okay, yn of t, y2 of t, y1 prime of t, y2 prime of t, yn prime of t, and finally y1 n minus first derivative of t, and yn n minus first derivative. Good. And we know that this is non-zero for some t in this interval, where the coefficient functions are continuous. Okay? So they represent a linearly independent set of solutions. Okay, I will finish the lecture giving a summary. So look, for some t in this interval, okay. So to sum up, consider the homogeneous linear ODE of order n. Good? That is, I consider this equation in the short form. Okay? Homogeneous form. Now, there exists, we say that the solution, the general solution, is the linear combination of n independent solutions. So y of t is C1, y1 of t, C2, y2 of t, Cn, yn of t, where C1, C2, Cn are arbitrary linear combination constants, and y1, y2, yn are linearly independent solutions, okay? Whose Wronskian determinant is non-zero for some t. Good? So we have to find the n linearly independent solutions. Please be careful. I say that each one is a solution of the homogeneous system. So the combination is also a solution of the homogeneous system. Okay? And the set, sometimes the set of functions, like this one, y1 of t, y2 of t, yn of t, is sometimes called a fundamental set of solutions, or fundamental set of solutions. Okay? That is, Wronskian determinant of these n functions so defined must be non-zero for some t0 in alpha beta interval. Okay, there is one more result. To finish, let's say that Abel's formula or Abel's theorem for this system, okay? A of Tx for this system, where A is the coefficient matrix like that, A11, A12, A1n in general, A21, A22, A2n, AN1, AN2, ANN, all may be functions of T, that coefficient matrix which are in general. They are functions of T, functions of T, functions of T. Okay? Now, we know that the Wronskian determinant of a fundamental matrix, of any fundamental matrix, can be given in this form: C times e to power integral of trace A dt, where C is some constant. Usually non-zero for linearly independent system. Okay? So this is known as Abel formula. So Wronskian determinant is C times e to power integral. What is the trace of this coefficient matrix? Look, trace is this: A11 of T, A12 of T, ANN of T, dt. This is very well known from the sum of diagonal entries is called the trace of the matrix of the square matrix. Good. So this is known as Abel's formula. If you recall that matrix A in corresponding to a linear ODE of order n has that form. So in the case of linear ODE of order n, A is, what is A? Recall 0, 1, 0, 0, okay? 0, 0, 1. So all diagonal entries are 0, except this is 0, 1. And the last one, what was it? Minus A1, minus A2, and minus A n minus 1, isn't this?
From minus A and minus.
Yeah, sorry. A n minus 1, A2, and finally A1 all have negative sign. Is this? So the Wronskian determinant is so defined so that so in this case, look, in this case of a linear ODE of order n, the system representation has this coefficient matrix, and therefore trace A, the trace of this matrix is what? Simply minus A1 of P, coefficient of n minus first derivative term. Therefore, this Wronskian determinant, Wronskian determinant of y1, y2, yn, okay, has this form: C this determinant minus A1 of t dt. Okay? We'll recall that our equation has this form: yn A1 of t yn minus 1 A2 of t yn minus 2 an minus 1 of t y prime an of t y equal to 0 for the homogeneous case. So what is A1? A1 is the coefficient of yn minus 1. Okay? It is the coefficient of n minus first derivative of 1 appearing in the linear equation. Okay? So the Wronskian determinant of the solution must be precisely in this way. Okay, let's stop at the end.